Okay, first, make sure that you are in radian mode. Okay, so on your either your graphing calculator or your 36 Pro. So mode, make sure you're in radian mode, and here mode, make sure you're radian mode as well.
Do you have one?
Yeah, it's called.
Okay, I think it's also helpful if you have, if you can have your summary sheet out as well. You have your graphing calculator summary sheet, but also the back has first theorem calculus integral definition that I want to go over with you as well. So, okay, so let's start with number one. Number one reads, a particle moves along the y-axis with a velocity given by v of t. Okay, in which direction is the particle moving at time t equals 1.5? So this particle, imagine it's moving along the y-axis. It can only do three things, okay? It can stay motionless, which is velocity 0. It can move up, which is positive velocity. It can move down, which is negative velocity. Okay, so we'll keep those numbers in mind. It says in which direction, up or down, is the particle moving at time t equals 1.5? We have the velocity function, so we can simply insert 1.5 in for t and find whatever that value is. Right? If it's positive, we know it's moving at that velocity, either up or down, depending if it's positive or negative. Okay, so now we're just going to enter that in on the, you can just enter it in as you see it, right? So x sine or 1.5 sine of 1.5 squared. Now make sure that you're careful where you put that exponent. The exponent is going to be inside the parentheses, not outside. It doesn't feel like a big difference, but if you put it outside, it's going to square the entire sine function. We only want that 1.5 squared. Okay, you can do the same thing on the graphing calculator, but I do want to show you a bit of a shortcut for future reference because on the graphing calculator, if you're having to call the function over and over again, let's say you want to evaluate a point, and then the next is asking for you to find the derivative at a point, and then the next is integral. If you're having to keep calling the same function over and over again, sometimes it's nice to just be able to reference it rather than having to type everything from scratch. So here, what we're going to do on the graphing calculator, if you would like, is you can enter everything in like how we did on the 36 Pro. Or you can have y1 hold that function, and whenever you need it, you just keep calling it, just keep referencing it. So I want to show you how to do that. If you go to y1, top left-hand corner of your calculator, type in that function x sine x squared. Now, on your paper, it says t sine t squared. But on your calculator, you're always going to use x. Okay. Never use a different variable than x. Try to match the variable as the one on paper. The calculator will complain. Okay, it's not going to either. It'll give you an error message, or it'll give you a value that's not correct. Okay, so always use x. So if I did x sine x squared into my graphing calculator, you go back to your home screen. So if we do second mode, it'll take back to your home screen. Now I'm going to call the function. Okay, on your calculator sheet, I highlighted the steps here. It says vars y vars function 1. That will allow you to pull that x sine x squared from y1. So if we go to vars. There's that button there, next to clear. Scroll over to y vars, and then function, and then y1. Now, if you put parentheses 1.5, what it's going to do is going to take 1.5 and it's going to insert it into the x of everything within x sine x squared. Okay. Anybody have any trouble pulling that value up? Okay, so again, you're going to go to x bars, y bars function from your home screen. That will pull y1, and then you don't have to keep typing in. If you're having to evaluate a different point, you don't have to keep typing that function in every time. Okay, questions? Okay, so let's look at, we'll finish that off here. So part A. Okay, v of 1.5 is 1.167. Now that's a positive velocity. So we know the particle is moving up. Since velocity is greater than 0, right? In this case, up is positive velocity, down is negative velocity, and 0 is object motionless. Okay, part B, find the acceleration. What's the relationship between acceleration and velocity? Acceleration is the what of velocity? Derivative, right? So we can find the derivative of velocity and then plug in 1.5. Now, if we were to do this by hand, what would be needed if we were to find the derivative of velocity here? We were from first semester. Okay, trig rules. What else? Yeah, there's also a product rule there. F prime g plus f g prime. But we have the calculator. We'll make the calculator do that for us. Okay. So there's a particular feature in both calculators that will allow you to find the derivative at a point. Okay. Maybe not the derivative function, but it will evaluate the derivative at a point. So on your 36 Pro, you see there's that d over dx button there under a natural log. Do second. Now I'm going to plug in that velocity function and then ask it to tell me the derivative or the acceleration when t is equal to 1.5. So x sine x squared. So what it's going to do is it's going to find the derivative and then plug in the 1.5 in for us. Okay. On your graphing calculator, if you do math 8 will take you to that same derivative feature, d over dx. You can type in x sine x squared again, or if you have it stored under y1, go to vars, y vars, function y1. So this is the same thing as x sine x squared. I just don't have to type it in every time. I can just keep calling it every time that I need it. Okay. Anybody have any issues with pulling those keystrokes? Yeah. Oh yeah, degree. Make sure you're rating mode. So yeah, go to mode. Go to rating mode. Yeah, on the AP exam, it's going to be all radian mode. Like you're never going to touch degree. So, like literally the day before the AP exam, I'm going to ask you guys double check your calculator and make sure it's in radian mode, because it will be. Yeah, sure. So the graphing one, you're going to go to math 8. Got that? Okay, d over dx. And if you have the function stored under y1, you're going to go to vars, y vars, function y1. And then you're going to plug in 1.5. Yeah, 36. You're going to go to second d over dx. And then just type in everything that you're asked to find. X sine x squared, and then x equals 1.5. Yeah.
Can you show where you're doing the graphing calculator to remember what model?
Right. So on your summary sheet, you're going to go to vars, y vars, function 1. All right. So that's our acceleration. Now, part B, it says, find the acceleration, and then is the velocity increasing at t equals 1.5? Okay. You see the word velocity there, but it's not really asking about velocity. It's asking about acceleration, because you see that this is the rate of change of velocity, which is really acceleration. So we see acceleration is negative. So since a of 1.5 is negative 2.049, okay, and that's less than 0, since acceleration is negative, the velocity must be decreasing. Okay, any questions there? Okay, part C, go ahead and put a star next to part C. You're going to see this a lot. AP exam loves to pull this type of question. It says, given that y of t is the position of the particle at time t, and that y of 0 equals 3, find y of 2. So this is basically a rearranging of first theorem. If you look on the back of your formula sheet, I put the variations on the back there. If I rearrange first theorem, I can rearrange it like this. And I can say, anytime I'm looking for a final location or final position, it's the same as starting with my starting position or given position. Your initial position is usually given to you, plus how much progress you made between those two endpoints. So the definite integral from a to b of v of t is displacement. That is basically how much forward progress this object is going to make between time A and time B. So I'm going to write that formula here, and we're going to adapt it for this problem. So it says, given that y of t is a position, and that y of 0 equals 3, find y of 2. So I'm looking for y of 2. I'm starting at y of 0. And I'm figuring out how much progress did I make between time t equals 0 and time t equals 2. And that's displacement. Okay, you know y of 0 is 3, so there's not really any calculation that needs to be done here. It's really with this piece right here, right? We want to find the displacement, how much progress, the area under the velocity is going to tell us how much distance that you're going to cover in that time period. So graphing calculator, you're going to go to that definite integral feature. So it's under E, see that second E there? You'll go from 0 to 2, and then type in x sine x squared. Okay, on your graphing calculator, do math 9, and then 0 to 2, and then you can do x sine x squared, or you can call that function again from vars y vars. Vars y vars function y1. So that's displacement. So that means between 0 and 2 seconds, this object is going to make a forward progress of 0.827 units. So we know that he's starting at location 3, and then he's going to travel 0.827 units in that 2-second period. So we know he's going to end up at location 3.827. Okay, so now part D, find the total distance traveled. So if you look on the second page of your summary sheet, evaluating total distance, you're going to get to that absolute value feature, and it's going to be located in math number ABS. Okay, so total distance. Formula is just the definite integral from A to B, absolute value of v of t dt. Okay, it's important that you put the absolute value just around the velocity function and not around the entire definite integral. Okay, so let me show you on the scientific here. Go to that integral feature there, second E. You're going to go from 0 to 2. So now you're going to get to that absolute value feature. Go to math. Scroll over to NUM number. And then there's that ABS. Absolute value. Type in that x sine x squared. It may take a second. Okay. On the graphing calculator, math 9, 0 to 2. Math number ABS. If you do vars, y vars function y1, you don't have, you just keep calling that function, not type in x sine x squared every time. So total distance is 1.173. Yeah, it takes a bit. Yes. Yeah, absolute value. You're going to go to math number ABS. Math, scroll over to NUM, and then ABS. Okay. Okay, now I want you guys to take a look at this here. The displacement is 0.827, but the total distance is 1.173. What does that tell us about what this object has done in that time period? Yeah, change direction, right? So if your total distance is different from your displacement, that means it's gone back and forth. The forward progress is not as much because total distance is kind of backtracked somewhere along that interval. Okay, so any questions with keystrokes on your calculator? Okay, so I've seen students, I don't think this is difficult in terms of displacement, total distance, and position, but it is easy to mix them up. So I want to kind of talk about the distinction between them because it is easy to mix them up. So I want to talk about some distinction here. Displacement is just the definite integral from a to b of v of t. Okay, distance is just the definite integral of the absolute value of v of t. Now, if I'm looking for a final location, then I have to involve adding it to something. I got to add it to my starting position with displacement. And the reason that I bring this up is sometimes I see students, if I ask for displacement, sometimes students, they want to add that starting point, or if I ask for distance, sometimes students want to add that starting point as well. So make sure that you are clear about the distinguishing feature so you're not confusing when to add the starting position versus when not to. Okay, have it on the board there as well. Okay, so displacement is just the definite integral. Total distance is just the definite integral. If it's looking for final location and it gives you a starting point, then that's when you have to add it to displacement. Right. So I see students add that starting position to these two problems, and that's not going to be correct. Okay. All right, let's look at number 2. Okay, number 2 is a Riemann sum table of values. Temperature in degrees Celsius of the water in the pond is a differentiable function. So this is just it's telling us information, something about this graph here. It's telling us that this is a smooth curve. Differentiable function means that there's not going to be any holes or asymptotes or sharp turns. It's going to be a smooth curve. Every point you can find the derivative. Okay, so that's what differentiable function means. It's nice that they're giving us that information because we're kind of in the dark in terms of what's happening between each of these order pairs, right? So here, the table shows us the water temperature recorded every 3 days. So on day 0, the temperature is 20 degrees. Day 3 is 31 degrees, so on and so forth, and day 15 is 21 degrees. But we don't really know what's happening between each of the other the values that we don't see. Okay, they're just telling you that that's a smooth curve all the way through. Part A, use the data from the table to find an approximation for W prime of 12. Okay, what does that notation mean, W prime of 12? Yes, so we normally associate W prime with derivative, but we can't find the derivative of a table, right? But we can find slope, right? Remember, slope is just a fancy, derivative is just a fancy word for slope. Now, it's asking us to approximate the rate of change or the slope at 12. What information would I need to find slope? Yeah, just 2 points, right? So which 2 points would you choose? Yeah, so anything close to 12 is good enough, right? So you can choose any 2 points as long as it's close to 12. You can choose these 2 points. You can choose these 2 points. You can even make an argument for these 2 points. So your answer may be different, but it's asking for approximation, and you have 3 choices. Okay, but if you're using anything here, or if you're using these 2 endpoints, that's too far away. You have better approximations if we can get close to our source. Okay, so W prime of 12 is approximately, that's a squiggly sign there, change in temperature over change in time. So I'll use the last 2, but you can choose any of those, of the combination of 2 order pairs there. So 21 minus 22, that's -1 over 3. What's the unit of measure going to be? Good. Okay, so -1/3 degrees Celsius per day. So the way that we can represent or visualize what's going on is that on the 12th day, we know that the temperature of the water is approximately decreasing by 1/3 of a degree Celsius on that day. Okay, that's just an approximation. Okay, but that's, yep. Because it's just change in y over change in x, right? That's my slope formula.
Yeah, so do you take the value next over? Or do you use the previous?
Yeah, you can use these 2 points as well.
Okay.
Yeah, so anything close. So your answer may be a little different from mine, but as long as you're using any of these combination of 2 order pairs from these 3 points, you will get full credit. Okay. But if you're involving anything further away, then that's not correct. Now, I do want to point something out here. Notice that your degrees Celsius changed to degrees Celsius per day because we're changing what is being asked. We're changing the units, right? So anytime a derivative or slope is involved, you're going to be continually adding that denominator notation or that denominator unit. Okay, so anytime you find a derivative, it's going to be another per day, right? So if you find the derivative again, it'll be degrees Celsius per day squared. Okay. The reason why I want to point that out is because anytime that you involve the integral, it's the opposite thing. You're going to be stripping away from that denominator unit. So if I take the integral of W prime, this degrees Celsius per day will turn back into what? Where did it come from? Just into degrees Celsius. Yeah. So if you take the derivative, you're going to keep adding a denominator unit, if you take the antiderivative, you're going to strip away from that denominator unit. So degrees Celsius per day will turn back into degrees Celsius if you were to find the antiderivative. Okay, part B. Approximate the average temperature in degrees Celsius of the water over the time interval from 0 to 15 days using trapezoid approximation with the intervals of length in every 3 days. So average temperature, we just learned about something where we can evaluate average value. So average temperature is basically average value theorem. Okay, what are our A and B values? Yeah. Replace every A and B with 0 and 15. So we don't have a W of t function to plug in. So we're having to rely on approximation to get to that value. Okay, we want to use trapezoid approximation. So trapezoid approximation is where we're going to be adding a bunch of areas together, but a bit of a shortcut is that all the middle heights will be doubled because we have all these shared sides for trapezoid. So the area of a trapezoid across multiple trapezoids that have the same width is 1/2 width, and then we're just going to add up all the temperatures, but then double all the ones in between. But the ones at the end, we're only going to use once. Okay, but all the ones in the middle are going to be doubled. So I'm just going to show the calculation here, and then we'll skip to the calculator. So 1/15 starts this off, and then we go to our area formula. 1/2 times the width. The width is every 3 days, right? Every width of the subinterval is 3. And we're just going to add up all the temperatures. Those are the heights of our trapezoid. So 20 plus, we're going to double 31. We'll double 28. Double everything else except that 21. Okay, so let's just skip the calculator part. If we were to enter all this in the calculator, we would get 25.1 degrees Celsius. Okay, part C. A student proposes the function p given by 20 plus 10t e to the -2/3 as a model for temperature of the water at point time t. So basically, it's taking what we did for part A, and now we're going to have a much more accurate model because we don't just have information every 3 days. We're going to be able to find the temperature at any point between 0 and 15, either on the 2nd day, 4th day, or 6.5 days later. So we have a much more accurate model to use. Okay, and it says now find p prime of 12. Now we can involve our calculator and derivative because now we can find the exact rate of change on the 12th day rather than just approximating using information around the table. Okay, so p prime of 12. We're going to make the calculator evaluate the derivative for us. So we're going to go to that Math 8 feature, or in your scientific calculator, that d over dx. Type in your function, 20 plus 10 x e to the negative x over 3. X equals 12. Okay, on my graphing calculator, I'm just going to store it under Y2. If you want to enter everything on the home screen, you can. It's just that I'm going to call it twice. I don't want to type it in twice, so I'm going to have it stored under Y2. So 20 plus 10 x, sorry, 10 x e to the negative x over 3.
How do you get the E?
Yeah, to get to the e, you're going to go to second ln. That first column of buttons there. Okay. Okay, so there's my function. I'm going to go back to my home screen. Math 8, d over dx. I'm just going to call that function. So vars, y vars. And then I want to find the slope or the rate of change on the 12th day. It's e to the negative x over 3. Right. And the reason I'm doing this is because I'm going to need it again for part D, so I don't want to keep typing this in again. So we have a more accurate. Before, our approximation was negative 1/3, but now we have an exact rate of change. So we know that on the 12th day, temperature of the water is decreasing at negative 0.549 degrees Celsius per day. Okay, part D, find the average value. So we're doing the same thing as part B, it's just that now we have a function to enter in for the integral rather than using geometric shapes and using geometric approximation. Okay, so your graphing calculator or scientific calculator can do second integral from 0 to 15. Type in that function that you pulled from before. Okay, make sure that you don't forget about that times 1 over 15 or divided by 1 by 15, either way. So your average temperature is 25.75 degrees. Okay, graphing calculator, math 9. I'm going to just call vars y vars. I already have it stored under y2. Okay, divided by 15. Okay, any questions? Yes. The reason why is because average value has that times 1 over 15. So when we plug in the calculator, we only found this integral here. We still got to involve this times 1 over 15, which is the same thing as divided by 15.
But we didn't do that for like part D.
We But this is average value, though. This is the average value theorem.
Oh.
Right, average value theorem, yes.
So since something like integral, it would be like the area under the graph, right?
That's right, that's right.
Isn't that graph like representing the? I don't know how to the graph is representing like the current value. So why would we use that to find the average value?
The reason why, okay, so you're making a good point here. This integral is going to change it to, it's going to change this P of T from temperature to degrees Celsius squared, right? Okay. But then you're dividing by 15. So as you divide by 15, it's going to bring it back to the notation for P of T.
Okay. So for like average value theorem, putting it into the integral, we're never going to be time function. Never like in like a different problem, we would never be like
it depends on what it's asking. Yeah, but basically the average value is always going to match the average value that they're looking for is always going to match the units of that P of t, because we are taking the antiderivative, but we're immediately bringing it back down because we're averaging out. So we're stripping away that unit for integral and bringing and then dividing it by that time. That makes sense. So we are changing the units through that integral, but we're bringing it back to the original unit by dividing by 15. Okay, let's go to the next page. I want to at least start this last tab problem. Let's see. At 11:35. Oh yeah, sorry, my clock is off. Okay, so number 2. It says the graph of the function is shown consists of a semicircle and 3 line segments. Let g be the function given by g of x. So notice that this is something we haven't seen before. It's a definite integral of f of t dt. Okay. So something that I want you to keep in mind is that there's a relationship here between g and f. Okay, this is the f graph. So I want you guys to indicate this as the f graph. Okay, the definite integral of f of t is equal to g of x. That tells us that g and f are not at the same level, right? It takes an integral to bring my f up to g. So what that really tells us is that f is sitting at the derivative level of g. Okay, so the f graph is the derivative of g. So we know that relationship here. We know that g prime is the f graph. Right, the f is the derivative of g. Now, I want to show you using second theorem that this is true, because if I were to find the derivative, if I were to find g prime, I would essentially be taking the derivative of this notation, right? So I want to show you what that looks like. Now, think about second theorem. What's going to happen if I pair definite derivative and definite integral together? That upper bound is going to get inserted where? In for the t. Yeah, so it's f of x times the upper bound's what? Derivative, which is 1, right? So what's f of x times 1? Just f of x. So g prime is the f of x. So you can either use what you know about derivative integrals to make this conclusion, or you can just jump to second theorem and then be able to go through second theorem and convince yourself of that as well. Okay, so g prime is f of x. We also want to find g double prime. Okay, so g double prime. If g prime goes to g double prime, then f is going to go to what? F prime. So there's the staggered relationship between f and g, right? G prime is f, and then g double prime is f prime. So everything is just kind of staggered in terms of their relationship. Okay, so we're going to highlight these 3 because these are the 3 relationships and formulas that we're going to use for part B. Okay, part B says find g of 0, find g prime of 0, and find g double prime of -1. Okay, let's find g of 0 here. So to find g of 0, which relationship are we going to use? Yep, the integral, right? And they're telling us exactly what to find the area of. So g of 0 is just the definite integral from -3 to, you see that x there? We replaced x with 0. So we're going to be totaling the area using the graph. So the definite integral from -3 to 0, if you just look at the graph between the graph and the x-axis, is what we're trying to gather. Now everything is above the x-axis, so really if we just find the area of that region, we have the definite integral as well. Now, this is a trapezoid. We can do trapezoid formula, or if you prefer, you can always split a trapezoid into easier shapes. Okay, you can create a triangle and a rectangle out of that. I can find the area of the triangle and the area of the rectangle, add them up, and that will be my definite integral, right? So geometric shapes. Triangle is 1/2 base times height, 1/2 3 times 1. That's 3 halves, or 1.5. The area of the rectangle here is width times height, so 3 times 1, which is 3. 3 plus 1.5 would be 4.5. Okay, so we're just doing whatever the rule is telling us to find. Okay, next part, find g prime of 0. Okay, do we have a relationship for g prime? Yes, g prime is f of 0. We have to build that relationship because the graph is in terms of f, so we have to find that connection between f and g. So f of 0 is simply asking us for the ordered pair of the graph. So what's f of 0? 1. Okay, g double prime of 0. Right? We go through this formula, right? G double prime of 0 is equal to, I'm sorry, -1, my bad. G double prime of -1. The relationship is telling us that it's f prime of -1. I'm going to highlight f of -1, which is here. But how do we interpret this? What's f? How do we find f prime of -1? Find the slope, right? This is a nice line here. We don't have to worry about, it's not a sudden curve where we're going to have to approximate slope. We know the exact slope of this line because if I can identify 2 points, I can do rise over run to find the slope of that line. I can find those 2 endpoints. Those are easy points for me to identify. Rise over 1, down 1 over 3. So -1/3. Okay, let's see if we can do a little bit of part C. Any questions so far? Yes.
Well, I got like puzzle with it. Oh, never mind.
Yeah, so 1 minus 2 over 0 minus -3. Yeah, you get -1/3. Okay, let's go to part C. Now, part C says find all the values where g attains a relative max. Now, this is the derivative graph of g, right? So this is not the original g graph. We're not going to be able to say, oh, that's a relative max at -3, there's relative min at 0, relative max at 2. This is the derivative graph. So remember how we did first semester, how we interpreted a derivative graph in first semester? We'll do that same thing here. I like to label my graph here. Anything above the x-axis is going to show me where my original graph is going to be increasing. Anything below the x-axis will indicate where my original graph is decreasing. Anything on the x-axis is where slope 0 or my critical point is going to be. So to the side, I'm going to say g prime sign line. I'm going to create a slope sign line for g of x. I'm going to go from -5 to 4. What are my critical points here for my g graph? Okay, -4. Where else? Yep, 1. One more. 3. So these are where my graph is going to potentially hit a relative max, relative min, because those are where the slope zeros will be. I'll place them onto my slope sign line. And now I'm just going to pull information about the arrows and about how my graph is increasing or decreasing. Okay, what's my slope behavior between -5 and -4? Well, yes, it's located below, right? Look at location, so decreasing. Between -4 and 1, above the x-axis, so increasing. Between 1 and 3, still increasing because it's still above the x-axis. Okay, between 3 and 4, below, right? So decreasing. Okay, look at these arrows here. Can we tell where the relative max is going to occur? Yep, because the graph is decreasing, rising again, and it's only going to have a relative max if it increases and decreases, right? But there's a hill on this at 3. So we can say for part C, relative max at x equals 3 because G prime changes from positive to negative. Okay, part C is extreme value theorem. Part D is point of inflection. We're going to pull that from the peaks and valleys of our derivative graph. We'll pick up D and E tomorrow, and then we'll cycle through these 3 problems tomorrow as well. Help session this afternoon at 3:30. Tomorrow morning, 7:30. We're going to try to do as many of these problems in the packet. Encourage you guys to work through if you would like. The key is attached, so those 3 topics are the problems you'll see on the test. Thank you.